When you picture a modern passenger jet, you probably imagine a perfectly smooth white tube designed to slip seamlessly through the air. But if you look closely at highly specialized aircraft, the heavy lifters and the global freighters, that sleek aerodynamic profile disappears. Instead, you find strange industrial features. You'll see oversized blisters bulging out of an Airbus nose, or bent front wheels on Russian cargo haulers, or a massive 28-wheel array that has to twist 90 degrees just to retract. Engineers accepted these unsightly shapes as a necessary trade-off for extreme operational utility, leaving behind visible evidence of a struggle against the laws of physics. To understand why these planes look so weird, we have to look at the specific environmental and physical pressures that forced these shapes into existence. The Airbus A330-200 freighter features a prominent blister jutting out from its fuselage, right under the chin. The problem started with the passenger version of this aircraft. When it rests on the tarmac, the standard A330 naturally sits with its nose pitched slightly downward. A sloped interior floor is a disaster for a dedicated freighter. Without a level deck, gravity pulls massive cargo pallets toward the front of the plane during loading, making it impossible to secure heavy loads efficiently. Airbus solved this by lowering the attachment points for the front landing gear, extending the leg just enough to push the nose up and level the cargo floor. This extension created a spatial conflict. The longer landing gear no longer fit inside the original bay. To keep the plane aerodynamic, engineers had to build a new external housing to cover the protruding gear. This unsightly chin is the geometric compromise that allows the A330-200F to function as a high-capacity global cargo hauler. Russian aviation employs an even stranger design. On massive haulers like the Antonov An-124, the landing gear looks visibly bent, appearing as if the struts might snap under the plane's own weight. Western aircraft typically use straight, vertical struts to save weight. This works well on pristine concrete, but it assumes the plane will never have to land on anything else. Russian cargo planes are built to survive the world's worst runways, from unpaved dirt strips to ice and degraded gravel. These aircraft use trailing link gear. This bent shape allows the wheel to act like a massive, heavy-duty shock absorber. When the wheel hits a bump, the pivot point allows the force to move upward and backward simultaneously. This geometry absorbs both vertical drops and horizontal forward shocks, preventing the airframe from destroying itself on uneven terrain. This jointed design also provides a secondary benefit. It allows the aircraft to kneel closer to the ground, lowering the ramp angle so it can swallow 150-ton payloads. This angled geometry turns a potential structural weakness into a survival mechanism for the world's most unforgiving runways. The Lockheed C5M Super Galaxy takes this complexity to the extreme with its 28-wheel landing gear system. At its maximum weight, a C5M would instantly crush standard airport tarmac if the load weren't spread across dozens of points of contact. But 28 wide wheels create a packaging paradox. Leaving them exposed in flight generates crippling drag, yet pulling them straight up into the belly would steal vital space from the cargo hold. The solution is a precise mechanical sequence. As the gear retracts, hydraulic actuators force each six-wheel bogie to rotate exactly 90 degrees horizontally. This turns a wide assembly into a narrow package that fits into a tight fuselage bay. The tolerances are incredibly tight. If the rotation timing is off by a fraction of a second, the massive gear assembly will collide with the airframe, potentially causing a catastrophic failure. This complex mechanical ballet is the only way to balance a 140-ton payload capacity with the aerodynamic efficiency required for long-range missions. The Airbus blister, the trailing link gear, and the rotating bogies are not aesthetic mistakes. Each of these features represents a calculated response to a specific, high-stakes operational limit. In extreme aviation, where machines are pushed to the absolute limits of weight and geography, form must always bow to function. When lifting off a dusty runway, engineers battling the laws of physics simply do not prioritize sleekness over a mission requirement. The next time you see an aircraft with a bizarre bump or an awkward stance, remember that those strange shapes are the exact reason that plane can land a 150-ton cargo load in the middle of a remote desert.